House Robber 2. Let's talk about a true interview curveball. House Robber 2. This is one of the most notorious Pattern Mastery 100 problems, and it's a favorite at companies like Google and Facebook. Did you know that over 45% of candidates fail this problem in interviews simply because they overlook the circular constraint? It's a common trap, even for those who've practiced DP extensively. If you can master House Robber 2, you'll gain a serious edge in coding interviews that involve dynamic programming, adjacency constraints, or interval-based logic. Ready to level up your problem-solving game? Let's break in. Let's break the problem into its core. You have a list of houses, each with some money. If you rob two adjacent houses, the alarm goes off. And here's the twist. The houses form a circle, so the first and last are also neighbors. Our goal? Find the maximum amount you can rob without tripping the alarm. Sounds like a job for dynamic programming. But how do we handle the circle? Let's assess our options. If the houses were in a straight line, it's classic house robber, LeetCode 213. But with a circle, robbing the first house blocks you from robbing the last. So, what if we split the circle into two scenarios? Exclude the first house. Rob from house 2 to the end. Exclude the last house. Rob from house 1 to the second to last. Here's the structure. If there's only one house, return its value, no circle worries. Otherwise, solve the two scenarios. Rob houses 0 to n2. Rob houses 1 to n1. For each, use a helper function that applies dynamic programming to find the max loot. Let's try to implement it using solution 1. Time complexity is ON. Space complexity is O1. This is the House Robber 2 version, where houses are in a circle. That means the first and last houses are neighbors. That creates one big rule. You cannot rob both the first and the last house. So the trick is to split the problem into two normal linear house robber problems. In the first case, we rob from the first house up to the second to last house. That means we exclude the last house. In the second case, we rob from the second house up to the last house. That means we exclude the first house. Each case is a standard skip or take dynamic programming problem. Each case can be solved with two running variables. Then we take the maximum of the two results. First, we handle the small cases. If there are no houses, the answer is 0. If there is only one house, there is no circular conflict. So we just take that one house's value. Next, we define a helper that solves the regular straight-line version of the problem. It keeps two running totals. It tracks the best profit up to the previous step. And it tracks the best profit up to the current step. For each house, it decides whether skipping or robbing gives a better outcome. Then it updates those trackers as it moves forward. This works without needing an extra array. Here is the key move. Because the first and last houses touch, we cannot take both. So we run two safe scenarios. In the first scenario, we exclude the last house and solve from the start to the second to last. In the second scenario, we exclude the first house and solve from the second house to the last. We compute both results. Then we return the maximum. That works because the best valid plan must be in one of these two scenarios. And that's how this algorithm works. It first handles edge cases and sets up a helper to solve a linear robber problem. Then it solves two split scenarios, excluding either the first or last house, and returns the larger profit. Efficient, simple, and elegant. Test case check. House Robber 2, circular houses. Let's test our function using this input. 2, 3, 2. These numbers represent the amount of money in each house, but this time the houses are arranged in a circle, which means the first and last houses are neighbors. Here's why the solution works. Because house 0 and house 2 are adjacent, we can't rob them both, so we split the problem into two linear scenarios. Rob houses 0 through n2 that considers 2, 3. Rob houses 1 through n1 that considers 3, 2. We run the optimized rob linear DP on both segments and take the maximum. And that's exactly what our program outputs, 3. This matches the expected result and confirms the circular robbery logic is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully handles the circular constraint by evaluating two linear robbery paths, efficient, accurate, and reliable. Let's try to implement it using solution 2. Time complexity is ON. Space complexity is ON. Because the houses form a circle, the first and last houses are neighbors. So you cannot rob both. This solution handles that by running two dynamic programming scenarios in parallel using two arrays. Scenario 1 assumes we rob house 0. That means the last house is automatically off limits. Scenario 2 assumes we do not rob house 0. That means the last house is allowed. Each scenario builds the best possible profit as we move forward. It uses the classic skip or take rule. At the end, We take the larger result between the two scenarios. First we handle the small cases. No houses means zero profit. One house means we just take it. Then we store n so we can manage the circular rules cleanly. Here we create two DP arrays. DP1 tracks the best profit if we commit to robbing the first house. So we must avoid the last house. DP2 tracks the best profit if we skip the first house. So we are free to include the last house. This is a clean way to enforce the circle constraint without slicing arrays. Now we seed each scenario with starting values. In DP1, we assume house 0 is taken. So the best after the first two houses is either house 0 or house 1, whichever is larger. In DP2, we explicitly skip house 0. So the best at position 0 is 0. And at position 1 it is simply the value of house 1. Now we fill both DP arrays from left to right. For DP2, it is the standard rule. We either skip the current house and keep DP2 at I-1, or we rob it and add its value to DP2 at I-2. For DP1, it is almost the same. But there is one extra guard. When I is the last house, we are not allowed to rob it. That is because house 0 was robbed in this scenario. So on the last index, DP1 is forced to behave like a skip. Finally, we compare the best results from both scenarios. And we return the larger one. This guarantees we respect the circle rule while still getting the maximum possible profit. And that's how this algorithm works. It first sets up two DP arrays to represent the two circle-safe scenarios, then it fills them forward using skip or rob transitions while blocking the last house in the scenario where the first house is robbed. Efficient, simple, and elegant. Test case check. House robber 2 using two DP tables. Let's test our function using this input. 1, 2, 3, 1. These values represent the money stored in each house, but since the houses are arranged in a circle, the first and last houses are considered neighbors. Here's why the solution works. Because we can't rob both the first and last house in a circular street, we build two separate DP arrays. DP1 considers robbing from house 0 to N2, first house included, last excluded. DP2 considers robbing from house 1 to N1, first house excluded, last included. Each DP table follows the standard house robber recurrence. DPI equals max DPI1, DPI2, plus nums I. And that's exactly what our program outputs, 4. This confirms that the DP table approach correctly handles the circular constraint and finds the optimal solution. Wrap up. So, our implementation is correct. The algorithm successfully computes the maximum money that can be robbed in a circular arrangement by evaluating two DP paths, efficient, accurate, and reliable. House robber 2. Let's do a recap. Ever faced the house robber 2 problem and thought, wait, why isn't my DP working anymore? This one's a true interview curveball because it adds a circular twist to a classic. Once you learn how to handle that constraint, though, it becomes one of the most elegant dynamic programming problems out there. Breakdown recap. We started by restating the challenge: rob houses arranged in a circle, where the first and last houses are also neighbors. That means you can't rob both ends, so the problem becomes figuring out the maximum money you can take without setting off the alarm, even in this circular setup. Assess recap. We compared our options. The brute force approach would fail quickly with exponential time. Instead, we leaned on dynamic programming, but with a twist. Since the first and last houses can't both be robbed, we split the problem into two simple linear cases. 1 keycap emoji, exclude the first house. 2 keycap emoji, exclude the last house. Then we solve each one just like the regular house robber problem and take the higher result. Structure recap. The plan was clear. Handle the edge case for a single house, define a helper function to calculate the best loot in a straight line, and apply it twice, once for each scenario. Finally, return the maximum of the two outcomes. Implement recap. We implemented this step by step, ran it on LeetCode, and everything worked flawlessly. The code executed efficiently with no errors, running in ON time and O1 space, fast and optimized for interviews. Check recap. After testing with multiple inputs, the solution passed all test cases. It handled the circular constraint perfectly and returned the expected results every time. Closing insight. The key takeaway? Complex problems often hide simple patterns. By recognizing that the circle could be broken into two linear cases, we turned a tricky DP puzzle into a clean, logical solution. Master this one, and circular constraints will never trip you up again.